Hello everybody, I'm Jiayu from Shanghai DPDK team, and I am a software engineer focused on GRO and GSO development. I'm also the maintainer of GRO and GSO. And today my topic is accelerating packet processing with DPDK, GRO, and GSO. Let us see some background first. A major part of packet processing are performed on a per-packet basis. This application may be TCP/IP stack and firewall. And these per-packet routines, like header processing, have dominant packet processing overheads. Currently, reduce the packet number is regarded as the most efficient way to reduce the per-packet overheads. So let us see how many ways do we have to reduce the packet number. The first way we have is to use a large MTU size. Large MTU size enable one packet to carry more data so as to reduce the packet number. But it has a drawback. That is, MTU size depends on the physical link. We cannot guarantee all paths use the large MTU. And the second method, we can leverage unique features. Large Receive Offload, TCP Segmentation Offload, and UDP Segmentation Offload. Let me show you how this three feature works. As you can see, in the ingress direction, LRO can merge small received packets into fewer large packets, and the link can deliver these fewer larger packets to application. And in the egress direction, applications can directly pass the large packets to the NIC. And TSO and UFO are in charge of splitting them into smaller ones to meet the MTU demand. As you can see, these three features are very efficient because they do not cost any CPU cycles, but they do have some drawbacks. The first is the supported protocol are limited. They only support TCP and UDP. And second is not all NICs support these three features. And the third method is the software method. It's GRO. And the full name of GRO is Generic Receive Offload, which merges small packets into larger ones. And the Generic Segmentation Offload, GSO, splits large packets into smaller ones. Compared with the previous two technology, GRO and GSO have three advantages. The first, they do not depend on the physical link support. And second, they do not depend on the NIC support. And finally, they are able to support various kinds of protocols. To benefit DPDK applications like Open Switch, we provide our GRO and GSO implementation in DPDK2. Let us see their position in DPDK. As you can see in this picture, GRO and GSO are two standalone libraries in DPDK, and they are higher than the PMD driver but lower than the DPDK application. And GRO always works in the ingress direction, and GSO always works in the egress direction. What do these two libraries look like in DPDK? Let us see the library framework first. This picture shows the GRO library framework. As we can see, we have 5 kinds of external functions, which can be directly called by the application. And internally, we have many GRO types. Each GRO type is in charge of processing one kind of packets. For example, TCP/IPv4 GRO only processes TCP/IPv4 packets. And the input packets are passed to different GRO types by the packet type field in above. And for GSO, we only have one external function. But I also have many GRO types internally. One GSO type only processes one kind of packets, and the input packets are passed to different GSO types by the OL flag field in above. So how do applications use our library? I list some simple codes here. As you can see, to use the GRO library is extremely easy. We just need to call one function is enough. And for GSO, it's very simple too. One function is enough. For GRO, we provide 2 sets of API for different usage scenarios. This one is called the lightweight mode API, which is also was mentioned in the previous slide. The purpose of providing this lightweight mode API is to enable application to merge a small number of packets rapidly. Apart from this mode, we also provide a more complicated mode. It's called heavyweight mode API. To use this mode is more complicated. Applications need to create a context first, and then use this context to merge packets. And when they want to get the merged packet, they need to flush them from the context manually. The purpose of providing this mode is to enable applications to process a large number of packets with more fine-grained control. So after seeing the API design, let us see some algorithm. GRO library uses the resemble algorithm to merge packets, and GSO library uses the segmentation scheme to split packets. Let us see the GRO part first. To implement a GRO resemble algorithm, we have two challenges. The first one is a high-cost algorithm would cause the packet dropping, especially in a high-speed network. And secondly, packet reordering makes it hard to merge packets. For example, Linux GRO fails to merge packet when encountered the packet reordering. These two challenges require our GRO resemble algorithm is lightweight enough to scale fast networking speed, and our algorithm is also capable of handling packet reordering. To address these two challenges, we provide a key-based algorithm. As you can see, here is the algorithm workflow. For an input packet, we will categorize the packet into a flow first. If we cannot find an existing flow for the packet, we will insert a new flow and insert this packet in this new flow. But if we can find a flow for the packet, we will check all packets in this flow and try to find a label for the packet. If we cannot find a label, we will store the packet into this flow. But if we can find a label, we will merge these two packets together. For TCP IPv4 packets, the header fields used to present a flow include source and dest, IP address, MAC address, and ports. And besides, it includes TCP acknowledge number. And the header fields used to decide if two packets can be merged include IP ID and TCP sequence number. If two TCP IPv4 packets want to merge, they must have the same flow value, and their IP ID and sequence number must be incremental. As you can see, our algorithm has two characters. The first is very lightweight. This is because classifying packets into different flows to accelerate packet aggregation is simple. And the second character is storing out-of-order packets, making it possible to merge it later. So our algorithm can mitigate the impact from packet reordering. So our algorithm can address the challenge 1 and challenge 2. Let us see an example. In this table, we have two flows, flow 1 and flow 2. And there is one packet in flow 1 and two packets in flow 2. Now here comes a new packet, P3. The first step in our algorithm is to try to find a matched flow. As we can see, F2 is a matched flow. So we will check all packets in the F2. As we can see, the IP ID and the sequence number of P2 and P3 are incremental, so they are labels. We'll merge them together. That's all for the GRO resemble algorithm. So let us to see the GSO segmentation scheme. This picture shows the segmentation workflow. For an input packet, we will split the packet payload into smaller parts first, and then add the packet header to each part. After these two steps, we will get many GSO segments. And finally, we will update the headers for all GSO segments. There is a very important question in this segmentation scheme. This is how to organize a GSO segment. As you know, the simplest way we can copy the header and payload to generate a new packet. But too many memory copy operations will hurt system performance. So in our GSO in our GSO scheme, we use a zero copy-based approach. In our scheme, we use two-part mBuf to organize a GSO segment. This picture shows the two-part mBuf structure. As you can see, one two-part mBuf include a direct mBuf, which is used to hold the packet header, and many indirect mBuf, which do not hold any data but just point to a packet payload part of the packet to segment. Using this structure to organize a GSO segment, just need to copy the header. We do not need to copy the payload anymore. Let us see an example. In this slide, we have one packet, and assuming it can be split into two segments. So we need two-part mBuf to organize the two GSO segments. And in the first step, we will copy the header into the direct mBuf. And then we will attach the indirect mBuf to the packet, and then make it point to the correct payload position. And finally, we will reduce the reference counter of the packet to segment. After this step, when all indirect mBuf are freed, the original packet will be freed automatically. To measure the GRO and GSO performance, we also have done some simple experiments. In our tests, we use this physical topology for GRO and GSO experiment. As you can see, this is in one server. And we have two physical interface ports are physically connected. And we use test PMD as a user space switch to forward packets between a physical interface and we host a user port. And in our test, we use iPerf to generate TCP IPv4 workloads to test the GRO and GSO. To set up the GRO experiments, we run iPerf client on the physical NIC and iPerf server on the VM. The iPerf client will send small TCP IPv4 packets, and our DPDK GRO are performed on the packets received by the NIC1. And to compare Linux GRO performance, we will also enable Linux GRO for the virtual LED port. And for GSO, we run iPerf client on the VM and iPerf server on the physical NIC 00. Large TCP IPv4 packets will be sent by the VM, and our DPDK GSO is performed on the packets sent by NIC 1. And to get the Linux GSO performance, we enable Linux GSO for the virtual LED port. Let us see some data. In this slide, you can see two figures. The left one describes the iPerf throughput improvement of DPDK GRO over low GRO enabling. And as you can see, our performance is 2.7 times than low GRO enabling. And in the right chart, it describes the iPerf improvement of DPDK GRO over Linux GRO. Our performance is also up to 1.9 times. And we have two fingers for GSO2. And compared with low GSO enabling, our performance is up to 2.2 times than low GSO enabling. And compared with Linux GSO, our performance is 1.5 times. As you can see, our DPDK GRO and GSO library can improve the iPerf throughput greatly. So maybe you can use our library to improve your application performance. Thank you. That's all for today's talk. Thank you. So any questions?
Okay, one question for GRO. You mentioned that you were using MAC, destination source MAC and destination source IP, or maybe the transport layer ports to be the key. Yeah. So I'm wondering if the packet ingress packet is tunneling. So let's say Vexline or Genève is used. How that GRO function? Your library support those kind of traffic?
Currently, our GRO library only supports TCP IPv4 and no support for tunneling packets, but it's our plan to support it in the next release. If we want to merge the tunneling packets, the keys will include outer IP ID and MAC address.
Okay, thanks.
Congratulations on your wonderful implementation. I just wanted to ask you, how many contexts do you support?
Excuse me, I cannot hear you clearly.
How many contexts?
How many?
Contexts?
Excuse me.
Flows?
Source?
No. So if you go back a couple of slides.
Okay. You mean GRO or GSO?
GRO contexts.
Okay.
Right here. So you have to keep a context when you do GRO.
Please wait a moment.
So you can coalesce the packets together. Right here. Right? You're creating a context.
It means
Right here.
this one?
No, go up a couple. Right. So you do a key-based approach. How many keys do you keep around to find a flow?
I get it. It depends on the workload. You know, if the input packets are belong to many flows, so we will generate many keys.
So you'll keep increasing the number of contexts as the number of flows go up.
The key number depends on the flow number.
Okay, thanks.
Yeah, on the same lines, the flow table size, is it configurable or is it fixed? You maintain the hash of the flows, right, in the lookup?
Currently, we haven't used a very complicated structure, a data structure, to work as a table. This is because our algorithm should be lightweight. This is also I have mentioned before the GRO part. So if we use very complicated structure, maybe we can merge more packets, but we may cost more CPU cycles to merge it.
Okay, do you use a hash table?
No. We just use two array. Just array.
Oh, okay.
Yeah.
Is that configurable, the size of the arrays, using an API?
Excuse me?
Is the size of the array configurable using an API?
Yeah.
Okay. And I have another question for the GSO.
Oh, okay.
You mentioned you use indirect buffers, right? So for the GSO. So we've seen some issues with the PMD using indirect mbuffs. So I was just wondering whether in your tests you saw any issues using indirect mbuffs or no issues?
For the GSO, you can allocate a pool to store the mbuffs are all indirect mbuff, but you can also use direct mbuff to work as the indirect mbuff.
Mm-hmm.
Yeah.
But is that, how do you choose one over the other?
This is the parameter inputted by the application in our GSO API.
Oh, the mempool, okay.
Yeah.
And I have a last question. The performance numbers which you showed, the 2.2x and things like that, the DPDK versus the Linux GRO, I was just wondering, is the performance improvement due to the native DPDK enhancements, the acceleration like the PMDs, or is it due to your algorithm as such?
Can you repeat?
So is the performance enhancements due to the fact that it's DPDK application and it bring its inherent advantages like the PMD pooling and things like that? Or is it due to your algorithm that you get this acceleration 2.2x and things like that?
About the performance of the GRO, maybe I think it's more complicated. Maybe we can discuss offline. Okay.
Okay, all right, thank you.
Yeah.
I'd say that's probably the last question, I think, yeah. But very good discussion, and I think we can have further discussion offline, so thanks very much.
Okay.